Pritam has just joined and he will record. Sit. Very polite. Hello, Pritam.
I have started the recording. You can
Okay.
start.
Okay, so welcome to lecture 33
Yeah,
on
Pritham,
Riemannian
I have
Symmetric.
a small query. So, are you going to upload the next lecture notes also to Google Drive?
Yeah. So, Manada, we will discuss this thing later. Okay.
Yeah.
So, welcome to lecture 33 on Riemannian Symmetric space. In the last lecture, we gave some examples of symmetric spaces of compact type and Euclidean type. In today's lecture, hopefully, we will see the examples of Riemannian symmetric spaces of non-compact type. So for that reason, we have to really recall some of the facts from our previous lecture. So first, let us start from discussion. So let G be a Lie algebra over C. Then G has a real Lie algebra structure. That means if something is a Lie algebra over C, then it is clear that it is also a real Lie algebra over R. So when G has a Lie algebra structure, say GR. I am really writing this as GR and set theoretically this G is equal to GR. So now let J be the map from GR to GR given by this thing J of X is equal to I times X. X belongs to GR. So first thing is we have seen that J is a complex structure on the vector space GR. First thing is J is R linear and J square is equal to minus identity. That is J is a complex structure on the vector space GR. Second thing is if you look at this thing Ix, the bracket of Ixy is really I into bracket of xy. Is for all xy belongs to GR. I can write this as Jx comma y is equal to J x for all xy belong to GR. Now I have a definition. Let GR be a Lie algebra over R and a R linear map J from GR to GR is called a complex structure on GR. If so, this is first thing J is a complex structure on the vector space GR. And second thing is the J of xy is equal to J xy.
What is the relation capital G and small j?
This is a one J actually. I have really this. Sorry,
Okay.
this is capital J actually. For all xy belongs to GR. Okay. So this is the same thing, but we are defining the complex structure on the Lie algebra setup. So So let so let us use it first. Let J be a complex structure on a really algebra R. Here we define this thing a plus ib dot x, a plus bj x. This is for x belongs to gr and a plus ib belongs to c. So this implies so it is easy to see that this with its scalar multiplication defined above. Defined above. GR has GR possesses a complex Lie algebra structure. Complex Lie algebra structure. The GR becomes a complex Lie algebra. Okay, we call that and the complex Lie algebra structure on GR as GR. So GR has a complex Lie algebra structure, and we denote by it GR tilde. So if you look at this thing, this, okay, so if you look at this thing, GR tilde R means real Lie algebra structure of GR tilde. This is becomes GR. So this thing is not important. Now I want to mimic the same construction for complexification, which I have done for vector space setup. So let G naught be a real Lie algebra. So then G rar equal to G naught cross G naught is a Lie algebra over R with Lie bracket is given by this thing. You have to so this is GR is set theoretically product of G naught plus G naught, and the Lie bracket will be given by something like XY ZW. So this is a little bit important here. So you have to take the Lie bracket as XZ okay, so this Lie bracket will be XZ minus YW. This is really XW cross YZ. So really X, Y, ZW belongs to G naught. Okay, this is my Lie bracket. This is not just this is not like this thing. XY XZ. This is not equal to this thing SZ. This is not okay. So this is the correct Lie bracket on G naught cross. Okay, so let J from GR to GR be given by this. Given by this thing J of xy equal to minus of y comma x. So easy to check that J is a complex structure on GR. Therefore, GR has a complex Lie algebra structure. Structure GR tilde, right? So we call GR tilde to be the complexification Lie algebra G naught and is denoted by G naught C. So precisely, G naught C is really by definition GR tilde. So if you know little bit of Lie algebra and know little bit of tensor product, so algebraically we have this thing. G naught algebraically G naught C is equal to G naught tensor C over R. And actually Helgason uses this notation G naught C like this. But in the book, actually, you will find that something like G naught C. I am following Helgason, so for that reason, I am really writing this. So now, okay, definition. A real Lie algebra. Yeah, one thing I have. Let us write. A real Lie algebra G naught is called a real form or complex Lie algebra G if and only if G naught G is equal to G is isomorphic to G naught C. It's really isomorphic. Lie algebra isomorphic. So let G naught be a real Lie algebra. Yes, and G is equal to G naught C. Then every we have discussed this thing. Every x belongs to G can be uniquely written as x is equal to really y plus ij, which y belongs to G naught and j belongs to G naught. Conversely, let G be a complex Lie algebra and H be a real subalgebra of G that every x belongs to G can be uniquely written as x is equal to really y plus iz with y belongs to G naught and z belongs to G naught. Then, oh sorry, not G naught. Okay, sorry. Thanks. With this y belongs to h and z belongs to h, then this G is equal to really h complex equation of h. Okay. So these two things is going to be important. These two things are going to be important. Now I define some code. So now I define something called compact real form. A real form G not of a G not of a complexly algebra G is called a compact real form. If and only if G naught is a compact Lie algebra. We have defined this thing. What do we mean by that Lie algebra is compact? So that doesn't really mean that the G naught is compact. So because G naught is a vector space, it can't be compact. Okay, so this is equivalent to thing that if and only G naught is a Lie algebra of a compact Lie. So two things is very important in this regard. I have okay. So recall the fact one. I just wanted to. So let G naught be a Lie algebra over R. And let G is equal to G naught C. Suppose S is equal to really V1, V2, Vn is a basis of G naught over R. Then it is also clear that then S is a basis of G over C. So we have discussed these things. Actually, the dimension of G naught over R is same as dimension of G over C, and from there you have to use this one or two this fact to prove this. Actually, we have discussed these things. So fact one and fact two is something. So let G naught be a real Lie algebra. And let G is equal to really G naught's complex unification of G naught. And let GR be the real Lie algebra structure on G. So let S is equal to V1, V2, Vn be an ordered basis of. I am taking here ordered basis of G over C. Now GR is a real Lie algebra. So then S tilde you can take this V1, V2, Vn, J V1, J V2, J Vn is an ordered basis of Gr over R. And let T belongs to endomorphism of C over G, okay, and matrix representation of T with respect to this basis S is equal to really A plus IB, okay, with A comma B belongs to M and R. So then we have some matrix representation, okay. So then if you look at this matrix representation of T with respect to this S tilde, that is really A B minus B. Okay. So what I'm saying, oh God, I left this someplace here. Okay. So this, if matrix representation of T with respect to this basis S is equal to A plus IB with respect to this basis S, then matrix representation of T with respect to this basis S tilde is really A B minus B. So these facts will be used throughout, okay, and whatever results we have seen for this vector space setup, those things will be true, okay. So let Ritam, are you able to hear me? Tapendu?
Yes, Mother.
So let G be a D not be a real algebra. And let G is equal to G naught C. Let GR be the real algebra structure on G. So then first thing is really you have to take this BG not XY. This B is the killing form on G naught. BG naught is the killing form on G naught. BG naught XY. Equal to really BG XY. And this happens for all X comma Y belongs to G naught. Second thing is this B GRXY to real part of BGXY. This happens for L XY belongs to G. And since this G is equal to GR set theoretically, so we can add X, both X and Y belongs to GR, and this definition makes sense. So this is my proposition. Let G not be a real algebra. Let G is the complexification of G naught C, and let GR be the real algebra structure of G. Then first thing is BG naught X comma Y is equal to BGX comma Y for all X Y belongs to G naught. A second thing is BGR X comma Y is equal to real part of BGXY. A proof. Okay, so proof. So let S is equal to really V1, V2, Vn be a basis of G naught over R. Then S is also a basis of G over C. We have known that. You write here B an ordered basis. you understand this basis of G over C. Then okay, S is here now. Also this S tilde, this thing V1, V2, Vn, this thing JV1, JV2, JVn is an ordered basis. GR over R. So now, if you look at this thing, first thing I am proving, you look at this thing, add G naught X, add G naught Y. In G naught and G, those have same basis. And if you take this XY belongs to G, XY belongs to G naught, okay. So XY also belongs to a element of G. The Lie algebra thing, by definition, on G naught and G, those are same. And the bases are also same. So first thing is I am proving. So this, if you look at this thing, RG naught X, RG naught Y, this basis with respect to S, RG naught, sorry, RGX, RGY with respect to S, these are same. So remember, S is a subset of G naught. Now if you take the trace, then you will get this thing, G naught S comma Y. Okay. Taking trace on both sides. We will get this thing as BG naught S comma Y is equal to value BG S comma this XY belongs to G naught. Okay. Second thing is now second thing is, if you let RGX RGY is equal to over this S is equal to really A plus IB, where with A comma B belongs to M and R. Now I told you that that fact we have to use this fact. But if matrix represents some T with respect to S is equal to A plus IB, the matrix representation of T with respect to S tilde is this thing, AB minus B. So first, okay, so first let us write this. First you will get this thing, B of XY is equal to really BG of XY is equal to trace of A plus I into trace of B. So that means trace of A is equal to real part of BGXY. Okay. Now I use that fact which I told you just now. RGX, RGY with respect to S tilde. This is the G naught, GR. With respect to S tilde is equal to really A, B minus B. So that if you will take the trace, then you will get this B is a GR X comma Y 2 times trace of A, and trace of A is equal to the real part of BGXY. Hence the proposition. So Tapendu, is it clear?
Yes, ma'am. Clear.
Okay, so next proposition. Let G naught G GR be as in the previous proposition. So then the following are equivalent. First thing is G naught is semi-simple. This thing is G is semi-simple. And only this GR is semi-simple.
Mona, can you hear me?
Yes, sir.
I just got confused. Go back to the statement which you were writing.
Now,
This, this one. Okay. So G naught was the genuine real Lie algebra you started with. Then G is basically G naught C, right? Twice the real dimension. Is that what you meant?
yes, sir. Yes, sir.
And that fellow is actually GR when you think of it as real vector space. This is your
Yes, sir.
notation.
Yes,
So
yes,
G
sir.
is basically G naught C.
Yes. This one G naught. And G naught is the real Lie algebra structure. So I just okay. So just G naught is the real Lie algebra, and G is equal to G naught C, and let GR be the real Lie algebra structure of G. Okay. So I am just not writing everything. Okay. So proof. Yeah. Okay. Suppose so I want to prove this I implies 2. Suppose G naught is semi-simple. Okay. Now I have to prove that G is semi-simple. Okay. So let X is equal to really Y. X belongs to this okay, a radical of BG. So I have to show that this X is equal to 0. I have to show, since G is semi-simple, I have to show. So since G is equal to G naught C, since G is equal to G naught C, that means X is equal to really Y plus IZ. Okay. For some Y comma Z, this belongs to 0. Both Y and Z is belongs to 0. Okay. Now, so as X belongs to radical of BG, so this implies BG X W is equal to 0 for all W belongs to G naught, because G naught is a subalgebra of G. So this implies BG. So okay, so Y, I put this Y plus IZ there, BG YW plus I BG ZW. I use the linearity of bilinear form. For this happens for all W belongs to 0. This is 0 for all W belongs to 0. Now I apply that previous proposition. BG is equal to really BG naught. So this Y belongs to G naught and W belongs to G naught. So I and this belongs to G naught. This belongs to G naught. I apply that proposition. So this is really BG naught YW plus I BG naught ZW is equal to 0 for all W belongs to 0. Now this Y G naught is a real Lie algebra. Therefore, B G naught Y comma Y comma W, this belongs to R. This is a real number because G naught is a real Lie algebra. So this also belongs to R. So this implies this B G naught YW is equal to 0 for all W belongs to G naught, and B G naught ZW is equal to 0 for all W belongs to 0. So that will give you this Y is equal to 0 and Z is equal to 0. And this is because of the fact that RG naught is semi-simple. Hence, X is equal to 0 and G is semi-simple. And G is semi-simple. Now I want to prove this 2 implies 1. Suppose G is semi-simple. Simple, and let x belongs to radical of b0. I have to prove that yes. So this implies, okay, x belongs to radical of b0. This implies b g naught x w is equal to 0 for all w belongs to g naught, and b g naught x y is equal to 0 for all w belong for what for all w belongs to g naught. Now as g is equal to really g naught plus, so no. Okay, so now I will use this fact that bg naught is equal to bg. Sorry. So what I am saying that this x belongs to g naught and w belongs to g naught. I use this fact that bg naught is equal to bg. So this implies this bg xw is equal to 0 for all w belongs to g naught. So as g is equal to really g naught plus I g naught, this implies that bg xw is equal to 0 for all w belongs to g. So this implies x is equal to 0 as g is semi-simple. So hence this g naught is semi-simple. So this is 2i implies I is really. Thus we have shown thus I is equivalent to 2. Okay. So now I want to prove that G is semi-simple implies that GR is semi-simple. So 2 implies 3 I am proving. So let G is semi-simple. So this implies this. Okay. So let x belongs to radical of b0.
Oh no.
bgr is.
Let G be semi-simple.
Oh, let's yes, sir. Thank you. Let G be semi-simple.
I have a very small comment. When you write
Yeah.
a definition, you write like if. You don't write if and only if. I think so. I don't know. Maybe Savato sir can say something.
Definition if yeah, right, if I write sometime if and only, but okay, these are English, okay, so you can
I
manage.
just have one comment to make. Write IFF, saves time.
Yeah, yes. So let G be a let G be semi simple. Thanks. Let G be semi simple. So let what I am saying. Okay, so I have to show that GR is semi simple. That X belongs to really radical of BGR. Okay, so this implies this B G X Y B sorry BGR X comma Y is equal to 0 for all Y belongs to GR. Okay. So, but what is BGR XY? This is really 2 into real part of BGXY. This is equal to 0 and GR is equal to G. I can write for all Y belongs to G. Now, if so, I can erase this 2. So, this implies real part of BGXY is equal to 0. Now, putting Y by IY, we get this thing. The real part of BG x comma IY is equal to 0 for all Y belongs to G. Now I can get this thing. I can take this thing. I can come out. So real part of I BGX comma Y is equal to 0. So this will give me imaginary part of BGXY is equal to 0 for all Y belongs to G. So this will imply that since real part of bgxy is equal to 0 for all y belongs to G, this will imply that bgx comma y is equal to 0 for all y belongs to G. This implies this x is equal to 0. Hence, this GR is semi-simple. Now, so let GR is semi-simple. So this implies and let x belongs to radical of BG. That means BG x comma y is equal to 0 for all y belongs to G. And certainly this will imply that real part of BG xy is equal to 0 for all y belongs to G. And this will also imply that 2 into real part of BG xy is equal to 0 for all y belongs to G. That will give you that BGR xy is equal to 0 for all y belongs to GR. This implies that x is equal to 0 as GR is semi-simple. Hence G is semi-simple. So we have shown that this is the hence. So we have shown that this is actually hence 2 is equivalent to 3. So we have finished this proposition. This proposition is going to be important. Okay, so some examples, and first example you take let G is equal to really GLNC, and GLNC is really this is MNC. So let x belongs to G, then x can be uniquely written as x is equal to really A plus IB. Okay, this with A belongs to MNR and B belongs to MNR. Okay. So then this representation is unique. Okay, this is unique representation. And what is MNR? Okay, MNR is equal to really GLNR, right? Hence we get this thing. Hence GLNC is really complexification of GLNR. So let us write this isometric. Now I have another real. So GLNR is a real form of GLNC. Now I have another real form for GLNC. So let x belongs to GLNC. So then this x can be written as x minus x star by 2 I into x plus x star by 2i. That is x can the x can be uniquely written as in this form x minus x star by 2 I into x plus x star by 2i. This is a skew Hermitian matrix, and this is also a skew Hermitian matrix. So this belongs to really UN, and this belongs to UN, and this representation is unique. So hence you get this thing. Hence UN's complexification of UNC is really GLNC, and this is really GLNR. And but UN is a really Lie algebra of UN, capital UN, and UN, capital UN is a compact Lie group. So this UN is a compact real form. And this GLNR is not a compact real. This is a non-compact real form. Therefore, they have to really they are non-isomorphic. Okay. So second thing is second example I want to really do. This is really let G is equal to SLNC. So let X belongs to really MNC. This implies X can be written as A plus IB with AB belongs to MNR, and this is a unique way of writing. So X belongs to SLNC if and only if trace of X is equal to 0, and this is really equivalent to trace of A plus I into trace of B is equal to 0, and this is equivalent to trace of A is equal to 0 and trace of B is equal to 0. That means both A comma A belongs to SLNR and B belongs to SLNR. So therefore whatever you will get. So see, this belongs to SLNR and B belongs to SLNR. Hence we get something like this. Hence SLNC is really the complexification of SLNR. And if you look at this X belongs to SLNC, so let X belongs to SLNC, then you have really that X, you can write at X minus X star by 2 plus I into X plus X star by 2I. And this is because since X belongs to SLNC, you can check that this belongs to really SUN. This belongs to SUN. Okay. Hence, this SUNC is really isomorphic to SLNC, and this is really SL complexification of SLNC. So this is really compact real form, and another is non-compact real form. And one thing, so this shows that you have given a complex Lie algebra, you may have more than one real form. So now I always leave some places. Set. Okay. So this is the thing. Now I want to discuss an example, important example. So let Q belongs to GLNR. So let BR and BC let bilinear form. Okay, so this is not killing form. Okay, BR and BC be the bilinear form, non-degenerate bilinear form. Non-degenerate bilinear forms on Rn and Cn defined by Q. Okay, given any matrix in GLNR, you can construct a bilinear form by this Q. So precisely, so you can take BR XY is really X transpose Q Y. This X comma Y belongs to Rn, and BC XY ZW. You can take that Z transpose QW. ZW belongs to C. Now you can look at this thing, automorphism of BR. So this is really what? This is equal to A belongs to GLNR. Okay. So that A transpose Q A is equal to your Q. Now we have seen that this is a Lie group. You look at the Lie algebra. This is small odd BR. This belongs to X belongs to really small GLNR. So that X transpose Q plus Qx is equal to 0. Now you look at this odd BC. This is really A belongs to GLNC. So that A transpose Q A is equal to Q. A small odd BC is really X belongs to small GLNC, small GLNC. So that X transpose Q plus Qx is equal to 0. Okay, so so X belongs to GLNC. That means this implies X is equal to Y plus IZ for some with Y comma Z belongs to GLNR. So this Y and Z, this representation is unique always. So this X belongs to odd BC if and only if so Y plus IZ transpose Q plus Q into Y plus IZ, this is equal to 0. So this is really Y transpose Q plus QY. If you consider only real parts, I into Z transpose Q plus QZ, this is really 0. So this is implies Y transpose Q plus QY is equal to 0 and Z transpose Q plus QZ is equal to 0. This implies Y belongs to odd BR and Z belongs to small odd BR. Then you get this thing, but so therefore we are getting what? Thus we get, if you complexify this odd BR, then you really get this small odd BC. This is a very important fact. Okay? You will use some, you will apply this thing. So application. First, I take this thing, small on, okay, Lie algebra of on. If I complexify it, that becomes ONC. And what is the matrix Q here? Q is the identity matrix. And you know that Lie algebra of ON and SON are same because SON is the connected component of ON. And Lie algebra of ONC and SONC are these are really same because ONC not is equal to real SONC and ON not is equal to SON, and I am using that thing. So this implies this SONC is really isomorphic to SONC. Okay. So this is the first application. Second thing, if you look at this OP comma Q complexification of that, then you will get this OPQC. So what is O? What is matrix Q here? Q here is IP comma Q. Okay. Now this connected components of OP comma Q. Okay, so one thing I have also discussed this. So we have discussed this thing that OPQC is same isomorphic to OP plus QC. Okay, this is as we have discussed some isomorphism. So this implies what you will get, small OP comma QC is equal to really small OP plus QC. Okay, so this O are identical, but you understand this is a small O, but that is capital O. Okay. So now, hence we get what? So we get this OP comma QC this is isomorphic to O P comma Q C, this thing, and this is isomorphic to O P plus Q C. So complexification of this O P comma Q is really O P plus Q C. Now I have I have told you that O P Q naught is really SO naught. So let us write here. This thing O P Q naught is really SO naught P comma Q, and O P plus Q C naught is really SO P plus Q C. So hence you get this thing. Okay, so this is really SO naught P comma Q C is really SO P plus Q C. So thus we get what? Thus we get this thing SONC. This is really SONC. And this is isomorphic to SO naught P comma Q C. And here I have to take this condition P greater than V1, Q greater than V1, and P plus Q is equal to N. So this is my compact real form, and other things are non-compact real forms. Okay. Non-compact because okay. So this is the thing. God, I am always leaving some places. I do not know what is happening. Okay. So next example is really. So next application is important. This is you. If you look at this sp2nr C is really sp2nc. And what is the matrix Q here? Q is here. Q is equal to 0. The matrix Q is equal to here 0I minus I0. Okay, 0 minus I0. Sorry. This is the matrix. So now, okay. So complexification of sp2nr is sp2nc. And so let x belongs to sp2nc. Pay some attention here. This implies e to the power tf belongs to really capital sp2nc. So we have seen that this sp2nc is closed under conjugate transpose. So e to tx star belongs to sp2nc for all t belongs to r. Since this sp2nc is closed under, since sp2n comma c is closed under conjugate transpose. Okay, so that means this gives you e to the power tx star. This belongs to capital sp2nc. Okay, this for all t belongs to r. This belongs to x star belongs to small sp2nc, Lie algebra. Okay. Now, so let x belongs to small sp2nc. This implies you can write the x is equal to really x minus x star by 2 plus I into x plus x star by 2i, right? Okay. Now since x star belongs to sp2nc and x is also belongs to sp2nc, this belongs to really sp2nc, and this factor also belongs to sp2nc. Now already this was an element of un, so this belongs to sp2nc. Now since okay, so we know this thing. We know that This is, sorry, this is not UN, this is U2N. Okay, so this is 2N cross 2N matrix, not 2N. We already know that this SP2NC intersection U2N is really your capital SPN. This is the Maxwell compact sub-2N. So this, for that reason, small SP2NC intersection small U2N is really small SPN. So this is really SPN, and this is SPN. So once what do you get? Hence we get this thing. SPNC equal to SP2NC, and this is isomorphic to SP2NR. So hence we get the final conclusion. So hence we have the following facts. So let us write everything in this. So first fact is really you get this thing. So that this thing actually we get what let us write first the compact real form. So UN C is really GLNC, and this is really GLNRC. Second thing is SUNC is SLNC, and SLNRC. Third thing is what we got, SONC, really SON, this thing is okay, so not P comma QC, and here you have to make this restriction P plus Q is equal to N, P greater than equal to 1, Q greater than equal to 2. So, fourth thing is your SPNC is equal to really SP2NC and SP2NRC. Now this thing actually we have proved that this SON and SPN is really semi-simple for okay, so and if you look at this, okay, so since this thing SUN, okay, this you have to take n greater than equal to 2, and SON, this is really how you have to take n greater than equal to 3, because SO2 is always abelianly algebra. So SO3, SON, and this SPN, this is really n greater than or equal to 1, are semi-simple. So then, therefore, this thing SLNC, this SLNR, you have to take these things for n greater than equal to 2, and this thing SONC, so not P comma Q. Okay, SONC, let us write this as n greater than equal to 3, SO not PQ is P greater than equal to 1, Q greater than equal to 1, and SPN, SP2NC, right, 2NC, SP2NR, this is for n greater than equal to 1, these are semi-simple. Okay. So now I have to, okay, these are semi-simple. because how do you prove this SUN, SON, and SPN and semisymple? Because the Lie groups are compact and they have finite center, and that is, if a compact Lie group has finite center, then they are semisymple. So this is the one thing. Huh? Okay. Now, so now killing form. I am writing now. We will prove some of the uh,
So,
formulas.
Mona,
Yes, sir.
you are not saying that when you have a compact and a non-compact real form both, then the Lie algebra is semi-simple. That you are not saying.
When a compact and
Non-compact real form both exist, then G is semi-simple. That you are not saying. You are saying that
no,
because GLNR is a counter example we have.
no, yeah, GLNR is count. So actually, I am using that. Sorry, yeah, better. You have really asked this. See, the thing is, SUN is semi-simple. Suppose, okay, by that result, actually, I, okay, by this result, which I have really stated this proposition. But G is semi-simple if and only if G naught is semi-simple, if and only G naught GR is semi-simple. I am using this result. Okay, if SUN is semi-simple, so SUN complexification of SUN, there is SLNC is semi-simple. Since SLNR is a real form of SLNC, therefore SLNR is semi-simple. Similarly, this SUN is semi-simple, therefore complexification of SONC is semi-simple. That means SONC is semi-simple. Now, since SO not P comma Q are real form of that, this is semi-simple. And as I told that for GLNC, we have a compact real form and non-compact real form. But GLNC will not be semi-simple because UN is not semi-simple. Actually, since it is also trivial because everything, if you look at the center of these Lie algebras, UN, GLNC or GLNR, you will find that this is non-zero. Okay. So one thing, so remark, let us put that remark, UN, this thing GLNC and GLNR, these are not semi-simple. Because if one is semi-simple, other things are semi-simple, but you can find that centers are non-trivial. Now let us write this killing form. Okay, so I will use this first proposition. Okay, this proposition you use that thing. To that proposition. Yeah. Where is that? Oh, sorry. This killing form. There is some relation between. Yeah. This word. I will use this I. Okay, so this thing. Killing form of G naught and killing form of G is same. So first I will write the results. Then so let G is equal to really uh, GLNR or UN or GLNC. Then this killing form BGXY is equal to really 2n trace of xy and minus 2 times trace of x and trace of y. This is xy belongs to G. Okay, so for anything, if G is equal to GLNR, this result will be true. For x, if G is or UN, this thing is all true. Or if G is GLNC, this is true because one is the real form of other. So now second thing is let G is equal to really SLNR or SLNC or this thing is SUN. So BGXY will be 2n trace of xy. Third thing is, so let G is equal to SON or SONC or SO not P comma Q with P plus Q is really N. P greater than equal to 1, Q greater than equal to 1. Then BGXY is equal to really N minus 2 into trace of XY. And this is really where XY belongs to G, XY belongs to G. So IV G is equal to SPN or SP2NC or SP2NR. So then BGXY will be 2N plus 2 trace of XY. If XY belongs to G. Okay, so now, so we will prove this result later, but first we will apply this thing. So discussion. Okay, so now I understand. Discussion. Okay, so let G be Lie algebra listed in the previous page. So that this thing Bg is equal to some scalar multiple of the trace form. Bg into C times trace. Okay, so that let us write this thing. Bg comma xy is equal to C times trace of xy with C greater than 0. For instance, you can take this SLNR, everything n greater than equal to 1, then that will be fine. And here you can take this SONC with n greater than equal to 3, that will be do the work, and here n greater than equal to 1 we can do it. Okay, so that is the thing. So then Bg restricted to, if you look at this thing, G intersection Hn plus G intersection Hn, if you look at this thing, so this is always positive definite. So why? Because if X belongs to G intersection Hn, okay, what is Hn? Okay, what is Hn? So where this Hn is the set of all Hermitian matrix. X belongs to MNC. So okay, X belongs to MNC, so that X is equal to X star. So if X belongs to G intersection Hn, then Bg XX is equal to really trace of C times trace of XX, and since X star is equal to X, so I can write C into trace of X star X, and this is really is equal to 0 if and only this X is equal to 0, because C is a positive number. Okay, so this is the thing. Now we want to really give some example of non-compact Riemannian symmetry. So consider the following Riemannian symmetric pair GS. So let us write those things. First is really SLNR SON, and second thing is SLNC SUN SP. Okay, so SO not P comma Q. So let us write the real things first actually. PQ and this SOP plus what was the thing, SOP plus SOP, and this is really SP2NR Qn. This is really P greater than equal to 1, Q greater than equal to 1. And this V is really what? SLNC SUN. So VI is really SONC comma SON. V double I is really SP2N comma C, really SPN. Okay, so these are the some Riemannian symmetric pair, and for this thing actually we have defined what is the involution. This is really G inverse star, and for above three things, the involution is sigma G is equal to G inverse transpose. Right? So we have seen that this P, actually we have described this P. P is equal to really G intersection. In the case of a real thing, if for case 1, 2, 2, 3, we have this thing G intersection H, G intersection Sn, where Sn is the set of all symmetric matrices. But since this is a G consists of real matrices, so this is equivalent to really P G intersection Hn. So in all cases, we have really P is equal to G intersection Hn. Hence, this BG restricted to P cross P is really positive definite in all cases. Okay, P is equal to G intersection, hence BG restricted to P cross P is positive definite. Therefore, okay. So one thing we have to show that this Riemannian symmetric pair which we have listed above, this is actually effective Riemannian symmetric. Let G comma H be an effective Riemann JB HB RSP listed above. It is easy to check that this ZG is finite. So ZG is equal to really that will be plus minus identity. Okay, when the ZG is equal to finite. Hence G comma F is an effective Riemannian symmetric pair. Therefore, G comma H is a Riemannian symmetric space of non-compact type. Number G is an effective Riemannian symmetric pair of non-compact type. And G mod H is a RSS of non-compact type. Okay, so now let us see. So we have here actually we have to make some minor exclusions. For instance, SON, you have to really take this n greater than equal to 3, and here n greater than equal to 1, and this is really n greater than equal to 2, n greater than equal to 1, and here actually P plus Q should be greater than equal to 2. P greater than equal to 1, that's okay. This expression, and n greater than equal to 2. So hence we have really proved that G mod H is a Riemannian symmetric space of non-compact. We have two special cases. So special cases. This first thing is P is equal to n and Q is equal to 1, then this thing SO not n comma 1, this mod SON, if really it's n, is a RSS of non-compact type. And one thing, SL2 mod SO2, you know that this is really upper half plane. So this is a Riemannian symmetric space. Is the RSS of non-compact. So we have given some example, but something is more general thing is true. So fact. So actually we will prove this probably. If I will have time, then I will prove everything about these things, killing form and everything. But one thing I probably will not have time. So fact is, so this is the definition which always we take, that G be a non-compact semi-simple Lie group with finite center. Okay, so G be a non-compact connected semi-simple Lie group with finite center, and let K be a maximal compound subgroup. Then G mod K is a Riemannian symmetric space of non-compact type. So you need little bit of theory of semi-simple Lie algebra to prove this result. So if G is a semi-simple Lie group, then you have a semi-simple Lie algebra. Then at the Lie algebra level, there is a cut and decomposition, and you use some theory to prove this thing. So if you want to accept this fact, then you can produce more examples of Riemannian symmetric space of non-compact type. For instance, you can take this SUP comma Q, this thing S of UP cross UQ, this P greater than equal to 1, Q greater than equal to 1. So this is, and this is thing SP P comma Q, this SPP cross SPQ, P greater than equal to 1, Q greater than equal to 1. These are Riemannian symmetric spaces of non-compact type. So with this, I would like to stop, and if there is any question you can ask. So in the next lecture, what you will do, will actually, you see that this to prove a Riemannian symmetric space effective, you need to have some knowledge about this center, and this thing is to prove a something some Riemannian symmetric spaces of compact type, we need to have some knowledge of center. For that reason, we next lecture will be devoted to calculate center of the some classical Lie group, and I will describe a general method how to calculate the center of the matrix Lie groups, and then actually we will prove one or two to prove this killing forms of some GLNR or SLNR or SLNC. Then let us see what can be done. Okay. So with this, I would like to stop. If there are any question, you can ask me now. Annoy or Pritam, Manali,
Yeah, I have no question.
Samya, do you have any question?
I have a question.
Yes, sir.
Uh, are you going to prove that if G is a semi-simple Lie algebra, real,
Hmm.
then its complexification will always have a compact real form.
Well, I can do that, but I am not going to now. As of it is not in my plan. But if you
Okay.
want, then I can do one or two lectures.
I think if you do that, then many of these examples will actually get tied up together.
Yes, sir.
That-
Chaliye, I don't have much time with me because most of the things are left. Only examples I have discussed and little bit of Riemannian symmetric pair and some definitions I have done. But for
Okay,
instance,
then in that case you should go according to your plan. Okay.
yes,
What you are saying about the GLNC, the counterexample of is
Reductive. Not semi-simple, but reductive. That
what?
this what I was
Yeah.
trying to say is having that compact and non-compact real form does not characterize semi-simplicity. Am I audible?
yes, sir, you are audible.
Sanjay asked something, is it? I mean, who does Sanjay or somebody asked some question? That's why I answered. Okay.
Tapendu is that.
Yeah.
Tapendu. So,
Tapendu asked a question.
yeah, Tapendu.
And what point you are trying to make here? That the GLNC is counterexample. That's what I
Okay,
am.
okay. I understand. What I was trying to say is that having a compact real form and a non-compact real form both does not characterize semi-simplicity.
That characterizes real reductive
Because
regroup.
yes, this is a counter example, the number one. I mean counter example to semi-simplicity.
Thank you, Merv. Thank you.
Okay, so I am disconnecting.